everyone, and today we'll be talking about an important topic in programming, and that is pointers. So pointers is quite infamous because a lot of people get confused by it, but I'm here to tell you that pointers aren't actually as bad as you think they are, and they can be quite useful in programming. So let's start by saying what really is a pointer, and a pointer is just a variable that holds a memory address, and that's all a pointer really is. So pointers are not as complicated as you might think they are. Really, you just shouldn't overthink pointers. They are actually quite simple because at the end of the day, they just hold the memory address of another variable. Okay, so first of all, here I am in Paint just to show what exactly I mean. So let's say this is our RAM right here, and these numbers are our memory addresses, right? So we have 100, 101, 102, and 103, and 104, 105, and 106. And these are locations in memory, right? And these are values at that memory. So right now we don't have anything here, right? So let's say I create an integer. What happens is in somewhere in memory it actually locates this it actually stores this 5 here, right? And it allocates 4 bytes of memory for it, right? So I'll allocate memories from 100 to 103. I'll allocate 4 bytes of memory for the integer, and that's because integers can be quite large. So if we need to if we have a large integer, then it will allocate more bytes for it, and a long integer will allocate more than just 4 bytes. That equals the memory address of A, right? So this ampersand symbol means the memory address. And that is the first of the syntactical things, is this is the memory address operator as well. What's going to happen is the next place of memory here, which is going to be 104, this is actually going to hold the memory address of the variable A. So now, if we were to print pointer for some reason, we would actually get this 100. And because pointers also have a memory address, you can actually get a pointer to a pointer, and you can even go further than that if you really wanted to. So there are a lot of interesting things you could do with this. But one thing that we're interested in right now is, let's say we wanted to do something to this, and then we wanted to get the value at this memory address. So what we can do is we can use the star symbol, right, pointer. If we were to output this, this will actually get us this memory address here, which is 5. So that's what pointers actually do. They allow us to track our memory and our variables in a certain way. Because we're holding the memory address here, we can actually look up this memory address and find the value here. So it's already quite confusing because we have two more symbols here. We have the star symbol and the reference symbol. So the syntax is already confusing. But once you practice with it, it's actually not too bad. So this is all really a pointer is. It just holds the memory address of another, and now let's get into the actual code. Okay, so here we are in the code, and now we're actually going to create a pointer inside of our code. So let's say I wanted to create a pointer that is going to hold the memory address of an integer. So the way I would do that is just make our integer. So I'm going to call this a, and I'm just going to give it a value right now. I'm going to set it equal to 5. And now I create a pointer. So the way we do this is we state the type of variable we want to hold the memory address of, which in this case is an integer because we're holding the memory address of an integer. And to declare that it's a pointer, we use the star symbol in front of the integer. Well, at the declaration, we use the star symbol. And now we name it pointer, and then to set it equal to something, we don't make it equal to a like this, because it says a value of type int cannot be used to initialize an entity of type int star. So what we have to do is specify to the compiler that we want the memory address of this. So now, let me put a semicolon. Now if I output both a and if I output pointer, we should get 5 and we should get something for pointer. So let's see. So when we output it, we get 5 here, and then we get some random number. So that's actually the memory address of the variable in hexadecimal. So the pointer, and if we run it again, you'll notice that we get a different value each time. And that's because the memory of our value a just gets stored somewhere random in our memory, and we really don't have too much control of where it ends up in memory. But we do have control over like what we can do with that memory. So that's important to know. If you wanted it to be in a specific way, it might not happen. But one thing that is important to know is that if I create another variable called maybe like 7, and I'm going to create another pointer 2, and we're going to set it equal to the memory address of b this time, right? And I'm also going to output pointer 2. Okay, so one thing that's important to know is you might notice these values are very similar. And actually what's happening is that the memory of these two variables are being created pretty much right next to each other. When we create variables here on the stack, they actually do end up being pretty close to each other. So that's another thing to know. When you create a lot of local variables here, the memory actually will be somewhat close to each other. What if we want the value at the pointer for some reason? Well, we can actually do that by using the dereference symbol. So I'm going to do something quite nifty with pointer. Let's say I created another variable called c, right? And I set this equal to 6. Alright, now I'm actually going to get rid of this line because we don't need it anymore. So let's say we have a variable called c and it's equal to 6, right? What I can actually do is reassign pointer to be the memory address of 6, right? Or to be this, the memory address of c. And this should be expected. So now what we can do is if we want the value at this, what we can do is we can write std cout, and we use the star symbol again, and we write the pointer name. So in this context, when we're not declaring it, the star symbol means dereference. So it's the opposite of reference. Reference means get the memory address of, and the opposite of reference would be get the value at this memory address, which is what the dereference is. However, the syntax is confusing, and I think this is where the confusion for pointers comes, is because we're introducing a lot of new syntax now. But some practice with this, and it's honestly not too difficult to get. So just keep practicing, and just eventually you'll understand that dereference in this context, where you're not declaring, or the star in this situation where you're not declaring means dereference, whereas the star in this situation where you are declaring a variable means you're making a pointer. So now if we run this, we actually get 6 here, even though a is equal to 5. But what if I did something like this? So I dereference pointer, and I made that value equal to 6, right? Now what I'm going to do is instead of doing this, I'm actually going to output a. So recall now that what we've done, we've made our pointer hold the memory address of a, right? And now we're dereferencing that value and making it equal to c. So I wonder what's going to happen when we run this. So we should still get 5 for a, right? Well, if we run this, we actually get 6. And what's happening here is why pointers is essentially the base bone of why pointers are useful. Because we're holding the memory address of a, we can actually, when we dereference it, we can actually alter the value at the memory address. Meaning, we can actually alter this initial a value. So what's happening here is that when I dereference this, what it's actually doing is it's not just copying the value 5 there. What it's actually doing is it's looking up the value at the memory address of whatever is assigned to it, right? And then what we're saying is the value at that memory address, make it equal to whatever we passed in here, right? So if I wrote even if I wrote like 7, this would still actually work. It would give me 7. Because what we're saying here is that get me the value at this memory address and make that value equal to whatever I assigned it to. And pointer holds the memory address of a. So if we run through it step by step, once again, I'll just debug it, right? We have a, which is equal to 5, and now we have pointer, which is just equal to some random hexadecimal number, but if we click on it, it holds the value of 5. And now we want to dereference pointer, so we want to get the value at this memory address, which it holds this variable right here, which is it holds a, which is 5. And then now a is equal to 7 because we've changed the value at the memory address and the variable at that memory address was 5. Now let's go into another example of pointers and their uses. So to actually understand this, we need to understand lifetimes and scopes. So things that we create have lifetimes, right? And they're declared, the lifetimes are declared by these curly brackets. So you might notice we're getting an error here because a is undefined. Let's say I make int a equals 5 now. We're actually still getting an error because a is still undefined. And the reason is a is going to be gone after this scope, right? So, whereas if we made it here, this would be fine. Obviously this wouldn't compile because we have multiple declarations of a variable, but now it's fine because these two are in the same scope, meaning that it is still alive. As long as the variable is still alive, we can do stuff to it. However, the problems appear to come when we have to deal with functions. So, for an example, let's say I have a function that takes in an integer, and let's just say it does something to it. So I'm just going to call this actually do something. It's going to take in a variable, and for now we're just going to increment that variable. So now I'm going to create int a equals 5 again. We're going to do something to a, and then now we're going to output a. Okay, so now if we run this, we actually get 5. So what's going on here? Well, if you know how functions work, you might actually know that this a value is just getting copied into here, right? So what's actually happening is it makes a new integer, and then so let's just say b, and then it makes it equal to a, right? And what's actually doing here is b++. So how do we fix this? What if, because I want to do something to this variable through this function. So how would we fix that? What we can actually do is we can make this a pointer. And we can also, we can dereference this pointer and then increase that instead. And what we can do here is just pass in the memory address of a. Now if we run it, we actually do get 6. So what it's doing now is it's creating a pointer here. It's copying a pointer, and it's making it equal to whatever we passed in. In this case, it's making it equal to a, which is the memory address of a right here. And then what it's doing is it's dereferencing that pointer, and then it's just making it equal to the dereference pointer plus 1. As long as you understand how dereferencing works, this shouldn't be too complicated to you. So even though this pointer is still also going to die outside of its scope, we're still modifying our original variable because a pointer just holds the memory address of that variable. So when we dereference that pointer, we can actually alter the location at memory. And this is why pointers are very useful, because memory is so important, and it's great that we get to manage it like this in C++. So doing this, you could do a lot of stuff like that. So that is one important use of pointers. And this is also useful because this also helps unnecessary large copying, right? Because it just holds a pointer, it just holds a memory address, you're not actually copying that much. Let's say I had a class here, right? And it was just called, let's just name an example. And if this class held like an array of like 5,000 characters, let's just say it initializes all of them to 0, right? But let's say it holds like 5,000 here, right? I'm going to create another do something class. And this one is going to take in an example. And then let's just say this class just doesn't do anything. But the reason I wanted to do this is now because if, let's say I make an example class called A, and I just did something like this, and obviously this won't work either way. If we do this and we run it, it uses a lot of memory is the point, and it's giving us an error that says the function uses way too much bytes of stack, and that's because we're actually copying all of this, right? So if we actually make this a pointer, and then we pass in the memory address here, I wonder if we're still going to get that same error. So we still do, but this way is actually more efficient because, yeah, actually we don't get that error. We get the error, we get the warning here now because we're still allocating that right over here. But the reason we're not getting it here anymore is because when we create that, we're not actually copying that 2,000 bytes of data anymore. We're copying only the memory address. So pointers can actually help us be very efficient. But that's not it for pointers. Not even close. let's get into the real nitty-gritty of pointers now. Okay, so let's say we have this here, our previous example, right? And we're getting a warning here that tells us that we have too much on the stack and too much on the heap. But what does that mean? First of all, let's address what the stack is and the heap is. They're essentially the two biggest forms of our memory. So a stack is a sort of data structure where the first thing that comes in is also the last thing to come out. So the last thing in is the first thing out, right? It's essentially like a stack of like of plates or something, right? So let's say you have your first thing here, right? You stack something on top of it. To get to this one, you actually need to remove this one and then get to this one, right? But the way that it works is there's a stack pointer, which essentially moves a certain amount of bytes to get to the next variable inside the stack. And because of that, the stack is quite fast, but it's also quite small. And the other data structure is the heap. And the heap is a much larger data structure, but it's not as fast to access as the stack is. So, how do we allocate onto the stack, and how do we allocate on the heap specifically? So here we've allocated onto the stack. Anytime we create a local variable, it gets allocated onto the stack. How do we allocate onto the heap now? Well, we use the new keyword. And the way we do that is we make this a pointer, and we write example, and then we put new, and then the type. In this case, the type would be example. But for now, what I'm actually going to do is just leave this as this, and I'm actually going to do it with this array here. So how we would do it is if I create a constructor. By the way, if you don't know what I'm doing here, go ahead and watch the class video that is up before this video, because it'll actually be a lot easier to understand this example specifically if you watched that video already. If you know what you need to do with classes, that's perfectly fine too. Okay, so back to this. I'm going to make this also public, and I'm going to make a constructor, okay? Okay, so in this constructor, what I want to do is actually, I want to allocate some of this data onto the heap, because it's warning us that this is way too much to allocate onto the stack. So what I'm going to do is I'm going to make this, I'm just going to call this array, and I'm going to make it a pointer. And now what I can do is, like before, I can do array equals new, and then the type, which is int. And here, this would be fine, but if we want to make it an array, because you notice here that it's not an array yet, we do new int, and in square brackets we allocate the size here, 5,000. And then we can just say array equals 0. And now if we run this, we should see that the warning disappears because we allocated onto this heap. And the heap is a lot larger of a storage area than the stack is. So if you're ever dealing with large amounts of data, you can choose to allocate it on the stack. And what else we could do is if you have too much data in a class, you could also allocate classes onto the stack. So if I wanted to allocate this onto the heap, then what I can do is just do new example. Like this. With optional, because if you want to call the constructor, you need to specify your parameters in here. But this is, for us, this is optional because we don't have any. And now, this should be fine, right? Well, not entirely. So let's stop there. So we successfully allocated our data using the new keyword, which is called dynamic allocation, by the way, right? This is what we're doing it on during runtime. So you should only really be doing this. I know you Java programmers, listen up. You do not use new everywhere in C++. Do not think about it, because this is not a good idea. You should only use new when you really have a reason to use new, okay? An example would be in this case here, where we have to allocate so much memory that it would be a terrible idea to do it on the stack. But new can lead to a lot of problems. Number one, it is slightly slower than just using local variables, actually, so keep that in mind. Number two, you have to start to manage your own memory. What do you mean manage your own memory? I thought it just deletes the variables like you were talking about the scopes. Well, yes, except not really. With pointers, it's a bit different. Your memory doesn't get deleted for you, actually. Let's say I have, let me just get rid of this on the example, right? I'm gonna make the constructor here, say object created, and then I'm gonna, in the line here, and then in the destructor, so this gets called when the object gets deleted, I'm going to output object destroyed. And I'm going to capitalize D to be consistent. Okay, so what I'm going to do here is I'm going to create a temporary scope, and I'm just going to create an example object here that is just like normal. So we've allocated like normal. Now if we run this, we get object created and object destroyed, right? Now what I'm going to do is I'm going to dynamically allocate it using the new keyword. So this is going to be new example. And now let's run it. We only get object created. Our memory actually hasn't been freed for us. So how would we do this? Well, we need to use the opposite of new, which is the delete keyword. And what we write here is we just put delete, and then we put a, which is our object name, right? And now when we run this, it'll say object created and object destroyed. So delete frees the memory from time, or sorry, frees the memory from RAM, and we'll also call our destructor for us too. And the thing is to keep in mind though, is this is why pointers can be very confusing, and this is why you shouldn't use new unless you have a good reason. If you don't, you have to delete it in this scope essentially, if you want to create more, if you don't want a memory leak, that is, because if I try to delete a here, this won't compile because a is undefined. So it's really weird. This variable gets deleted from memory, but remember that a pointer is just a variable that holds a memory address. We're back at this again. So, because this is just a variable that holds a memory address, that pointer variable has been deleted, but the memory hasn't been unallocated yet because we used the new keyword. So, keep that in mind. Don't use new unless you have a good reason to. So that's the first thing about new. There are ways in the standard library that are called smart pointers that will automate your memory management for you, and honestly, you should be using those if you don't have a good reason to use new and delete, but there are times where you need to use new and delete, and there are times where smart pointers are more helpful. So keep that in mind. So what's one place where using new and delete is helpful? Well, actually in the data structure called linked list. And how linked list works is you have a bunch of nodes that hold data, and they also have a pointer to the next node, right? And essentially you have sort of a dynamic array. In that case, you need to use the new keyword. So let's look at a scenario of a linked list implementation. So, oops, I'm just going to get rid of this class example. And let's say I have a structure here. I'm going to call it node. And it's going to hold an integer, which is the data, and it's going to hold a pointer to the next node, right? This has to be a pointer, by the way. So now, what I do, right, is if I have I'm going to make it return a node. Actually, no. I'm going to make this void, and what it's going to be called, I'm just going to call it add. It's going to take in a pointer. It's going to take in a pointer to the head, and it's also going to take in the data we want to create, right? By the way, this is not meant to be a tutorial on linked list. If you're interested in this, I recommend looking at a tutorial about linked list. In fact, I might make one about data structures actually soon because I've been looking into that. But anyways, what we want to do here is actually create our own node, make it a pointer. I'm just going to call it temp. Oops, I'm going to use the new keyword here. Why do we want to do that? Because after this, if I'm allocating memory into a function here, in this case, I don't want it to delete after this function is over. I want that memory to still be alive. So that is what I'm using the new keyword here for. And I'm just going to do this, but we don't need it. We're going to say temp data. So this arrow symbol is it's essentially a shortcut, because normally, if you know from object-oriented programming, you would have to do like this, dereference it, and then do that, right? The arrow operator just does that for us. So the arrow operator just makes it so that we can just essentially use an object to get that. So we're gonna make the data equal to the data they passed in. And now what we're going to do is we're going to say if our head, if the pointer to our head, if our head not the pointer to our head equals null pointer, what we want to do is we want to, actually, no. this is actually not as complicated as I'm making it. Basically, what we want to do is set the next node in it to equal to the dereferenced head, and then now what we want to do is say the dereferenced head equals temp. If you're doing this, make sure you have a delete function, but for now, just for the sake of doing this, I'm just going to show you how it works. So now what I'm going to do is I'm going to create a node here. I'm going to call it list, and I'm going to set it to equal null pointer. Null pointer means that my pointer isn't pointing to anything right now. It's basically a way of like when we initialize an integer to equal 0, but then we initialize it later on, or by using the curly brackets. This is essentially the same thing. We're saying that this pointer right now isn't pointing to anything. And what we're going to do in it is we're actually going to call the add function. We're going to pass in the memory address of list. And the reason we have to do that is because what's going to happen is if we do this, it's going to create a copy of our head, right? And we actually want to alter the pointer, not the copy this time, right? Like similar to when we had the void do something function, if we were to alter a variable in there, it would not alter the variable we passed in because it would just create a copy of that variable. And that's why we have a pointer to a pointer here, because we actually want to alter the pointer in this time. So we're going to pass in the memory address, and we're going to say maybe put 3, and then maybe we'll add another thing that's 6, right? And now if we output list, we'll output list.data, and we're going to end line here. I can just do end line. And then we're also going to output the next data inside our set, and then we're also going to end the line here. Now if we run this, we get 6 and 3, which is what we appended, right? So this is a case where we want to use new. If we didn't use new here, then this entire thing would simply not work, because what would happen is this memory would get freed after this function call, and then boom, no more linked list. So that is why new would be important. This is a good situation where new is important. There's obviously a good time and place for new, but I would generally avoid it in certain scenarios unless you absolutely need to allocate on the heap, or you need your memory to last longer than the lifetime scope. Actually, I should probably mention too, if you create a pointer, if you want to make a like an array pointer, right? So let's say like this, and we use the new keyword here, and let's say we allocate like 200 or something, right? If we want to delete all the memory, instead of just running through all the pointers, there's a special operator like this, where you just put the square brackets after delete, and then you do this, and you'll notice that they turn blue, and that this is a special operator used for deleting it. So this will free all the memory here. And that's really a general tutorial on what pointers are exactly. I highly recommend practicing with them, especially the dynamic allocation parts can be quite confusing. And there are way more stuff to pointers too, like topics like polymorphism and stuff like that. And I think that's too advanced for me to cover right now. Polymorphism is a cool topic though, and I think it's actually really interesting, but it's a bit too much at this moment, so maybe I'll make a tutorial on polymorphism, or maybe I'll just cover it in the game series, one or the other. But yeah, so just keep practicing with pointers, and now that you know the gist of it, like once again, a pointer is just a variable that holds a memory address at the end of the day, and whenever you use new, you're dynamically allocating memory, meaning that it gets allocated not to the stack, into the heap, which is a larger but slightly slower place to store memory. And memory that needs to be stored on the heap also needs to be deleted too. It's really just in practice, pointers can be a bit confusing at times, but I'm sure if you practice, you can get the hang of it quite quickly. So if this tutorial was helpful for you, just like this video and comment on what do you think I can do to improve my videos, because I want to make my videos as helpful as possible. And yeah, that's all. So thank you guys for watching. Good luck and bye.